All right, so we discussed the resting membrane potential last time we met. And basically we talked about really breaking down that negative 70 millivolts, that number, and really deciphering exactly how that number comes about, exactly how that negative charge inside the cell is derived. And so to do that, we looked at the forces acting on sodium, we looked at the forces acting on potassium, and then we brought those two things together in conjunction with the sodium-potassium pump and the leak channels and the different permeabilities. All of that came together, and that resulted in a steady state of a resting membrane potential value being negative 70 millivolts. And in terms of the ionic movement, what that means is that there was more of a negative charge left inside the cell, 70 being the magnitude of that, and then there was more of a positive charge on the outside of the cell. So let's just review how we got there, and then we'll keep going, because as we speak about the resting membrane potential, this is really just the basis for the excitement, which is the action potential. So we're going to review how we get that resting membrane potential, and then we're going to move on and talk about how we can excite that and change that membrane potential value. Okay, so let's sort of set the scene here. We're looking at a neuron, right? Here's our soma. This is our axon, at our axon terminal. And so we know that at rest, a neuron has a membrane potential of negative 70 millivolts. So we're describing how did we get there? And what that negative 70 means is that inside this neuron, there's an abundance of negative charge. Outside that neuron, there is an abundance of positive charge. So all that we've been saying, all that we've been describing is to explain how we get this negative 70 value. So let's look a little bit further at the ionic movement to result in that value. So let's look at our hypothetical cell here. All right, the first thing we want to establish is that on the membrane of this cell, we've got the sodium-potassium pump. Okay, and that's going to be 20% directly resulting in the value that we get, that negative 70. All right, so 20% of that value is coming directly from the fact that we have a sodium-potassium pump, which is pumping 3 sodiums out. So let's illustrate this as sodium, and they are going out. And then it's pumping 2 potassium in. So this is our potassium, and they're being pumped in, right? And this is our sodium, potassium pump. All right, so 20% of that negative 70 just comes from the fact that we're pumping more positive charge out of the cell. The other 80% of that negative 70 is coming indirectly, because as we create the gradient by moving sodium and potassium, we now have a concentration gradient to leak ions in the opposite direction. All right, I think I accidentally asked someone to unmute. Please ignore that. I was just trying to make sure everyone's on mute. Okay, so our sodium potassium pump is on the membrane. The other thing we want to establish is the leak channels, because now we've got a concentration gradient created by the sodium potassium pump, and so ions can leak in the opposite direction. So we know that there's a greater permeability for potassium. So let's establish that here, and we will illustrate that by showing more potassium channels, right? And a lesser permeability for sodium, right? And so we're only going to put 1 sodium channel. So that's the first step in terms of really describing this. So step one is that we think about the differing permeability. So the permeability, which I'm going to represent by this large P, for potassium is greater than the permeability for sodium, right? In other words, there are more ion channels for potassium to leave. The second thing we want to now establish is the concentration gradient for both of our ions, right? So the concentration gradient, in other words, the CDF, or the chemical driving force. So let's look at what that looks like. And again, we're thinking about our sodium potassium pump and what it's doing. So because it is pumping potassium in, we've got a higher concentration of potassium inside our cell. Quite a few of these, and then very few on the outside, right? And then if we think about sodium, sodium has a higher concentration outside, right? Because it's actively being pumped out. So there's lots of sodium on the outside. And then very few on the inside. Okay, so let's establish that here. So potassium now has a concentration gradient that wants to move it into the cell. Whereas sodium has a concentration gradient that wants to move it out of the cell. I'm sorry, I flip-flop these. Let's undo all of this. All right, because we know potassium is at an excess on the outside, and so it's going to want to move. Potassium is at an excess on the inside, and so it's going to want to move outside. Help me here this morning. Okay. Outside the cell. And then sodium should be moving into the cell. All right. Okay, so finally we got this together. So sodium, greater concentration outside, it wants to move in. Potassium, greater concentration inside, it wants to move out. So that's our concentration gradient or our chemical driving force. Let's now look at the electrical driving force. All right. And I'm actually going to go and draw some large arrows so that you can see where potassium is moving according to the CDF. So according to the CDF, potassium wants to move out. All right, this is our CDF. According to the CDF, sodium wants to move in. All right, just so that this is really clear here, because we're going to add the electrical driving force as well. Okay, now as far as our electrical driving force, that is going to be based upon the polarity of the cell. It's going to be based upon the charge of the particle in question, as well as the polarity of the cell. So here, because we have established that potassium is leaving and it has more opportunities to do so, sodium is coming in with less opportunities to do that. There is going to now exist a negative environment inside the cell. All right, so we've got an abundance of negative charge being left behind inside, and then an abundance of positive charge in the extracellular fluid, right, outside the cell. So now we can really begin to think about the direction of movement of our EDF. So because both of these are positively charged ions, they're going to both want to get into the cell. Right? They're going to both want to get towards the negative area. Therefore, potassium will have an EDF moving it into the cell. Right? This is the EDF, electrical driving force. And then sodium will have an EDF also moving it into the cell. Okay, so let's describe that here. So potassium into the cell, and then sodium likewise into the cell. Okay, I hope everyone is with me so far. I'm going to pause and just make sure there aren't any questions popping up. Okay. So that is the two independent forces that are acting on our particles. And so now we're going to actually start putting these two pieces together. All right, we're going to have to add if they're in the same direction and then subtract if they're not. So as we think about the ECDF, right, the combined force, it's going to be out of the cell for potassium. Because if we think about the values of these two forces, the concentration gradient is a reflection of the equilibrium potential for potassium, which we know is negative 94 millivolts. The electrical driving force is going to be a reflection of the membrane potential, which we know ends up being negative 70 millivolts. And so if we think about the bigger number here, it's going to be the outward force. So the concentration gradient is bigger than the chemical driving force is bigger in terms of magnitude than the electrical driving force. So the overall direction of potassium will end up being out of the cell, but because of this opposing inward force, it's going to be very weakly so. So it's going to be a magnitude of about 24 millivolts total, and then an overall direction of out of the cell. Okay, so as we think about potassium, there is a weak force moving it out of the cell. A weak force moving it out of the cell. And then sodium is pretty straightforward, right? We've got the concentration gradient for sodium, again, reflection of the equilibrium potential for sodium, which is positive 60. And then again, our electrical driving force, a reflection of the membrane potential, that is negative 70 millivolts. And so as we add these two values together, because remember, if they're going in the same direction, we add the two values. So it's going to be a combined total here, which is a stronger force of 130 millivolts. And then both of these are going into the cell, so an overall direction of into the cell. And so that's going to be a strong force moving it into the cell. So potassium has a strong force moving it into the cell. Okay, and I'm going to put the values here just so that we can see the magnitude of this. So this is 130 millivolts in terms of the strength of that force. And then here we've got 24 millivolts. Okay, so this is how we establish the resting membrane potential, and this is how we generate that negative 70. So as we pump ions in one direction, according to the two forces we described, they're going to leak in the opposite direction. And then because they're balancing each other out, because potassium is moving more, it has a greater permeability, but it has a weaker force to do so. Sodium is moving less with a smaller permeability and a stronger force to do so. That ends up balancing out perfectly, and the sodium-potassium pump just keeps on reestablishing those concentrations, right? And so this ends up at a steady state, and the value at that point is negative 70 millivolts.